Guys, it's a differentiation property in Laplace transform, and we have a continuation to this property in Laplace transform. According to the definition, x of t will be given, and according to that definition for Laplace transform, this x of t is multiplied with e raised to minus st, and now this product is integrated from 0 to infinity and some other limits according to the property, and the resultant will be x of s. The resultant will be x of s, and the procedure is what? Yeah, this is the procedure. All right. If x of t is given, if we have to like x of t, the function x of t is given, and if we have to evaluate the Laplace transform of this one, this is the procedure, and the resultant is represented with x of s. What if we have the given function, it's x of t, but the first derivative d by dt of x of t. Now we have to find out the Laplace transform for this one, and is there any change in that procedure? No, the same thing. This function is multiplied like d by dt of x of t is multiplied with e raised to minus st, and now this product, like this one, it's considered as one factor, another factor. Now this product is integrated from 0 to infinity with respect to t, and so we have dt. All right. To carry out the further procedure, we'll have to like UV rule reflects over here, considering this factor to be u and this one to be v. We'll have to expand this making use of the UV rule, and the UV rule is this one, integral u v dx. It's the solution will be u comes as it is, multiplied with first integral of v, integral v dx, and we have the limits over here minus integral, and we have something, the factor dx, and inside this braces we have u dash, the first derivative of u, and multiplied with integral v dx, and this is the procedure for uv. The same thing, applying this uv rule over here, the next step will be, it says uv rule says, if you consider this to be u and this to be v, u comes down as it is, in the sense e raised to minus st, which is supposed to be u, comes down as it is, and integral of v dx, v is this one, this integral and this derivative gets cancelled, and we have x of t, the function as it is, with the limits, with the lower limit 0 to infinity minus integral here, first derivative of u dash, first derivative of u, in the sense e raised to ax dx, it will be a into e power x, isn't it? So in that way, minus of s into e raised to minus st as it is for this one, and integral v, this is v, this integral and this derivative gets cancelled, so we have that t as it is, and once again dt. Alright, so plugging in the limits, upper limit and lower limit, we have e raised to, in the place for t, substitution for t, isn't it? So infinity, we have infinite to be plugged over here, that will be minus infinity into x of infinity minus the lower limit, e raised to 0, x of 0 for the lower limit, minus, guys, we have a negative over here, multiplied, that will become positive, and this s is integration is not applicable for this s, that can be taken out independent of t, like integration, so that is taken out. Integral 0 to, I didn't plug in the integration limits over here, I'm sorry, integral, and x of t, making it in order, putting it in order, e raised to minus st and dt. All right, so guys, this will become 0, as it's well known, negative 1 by infinity, that is 0, and this term, this will be 0, e raised to 0, that is 1, and so we have minus of x of 0. All right, continuation plus s into this entire integration can be substituted with x of s, and this is for x of s. All right, in the sense, finally we have s into x of s minus x of 0. This is caps and this is lower. Please make a note of this one. It is initial value you'll come across while solving problems. All right, and yeah, this is all about differentiation property in Laplace transform, and making use of this one, this result can be extended to something else. what was that result? We started with the Laplace transform for d by dt of x of t, and this is the procedure. The procedure to carry out the Laplace transform, to evaluate the Laplace transform of the given function, and the result was s into x of s minus x of 0. All right, so making use of this result to evaluate something else, guys, substituting s tending to infinity on either side of the equation in the LHS and RHS also. What did I say? It's substituting for s tending to infinity on either side will give us some other result. All right, s tending to infinity on either side, in the sense talking about LHS, s tending to infinity will be plugged over here, that will be resulting into e raised to minus infinity, that will be 0, and the entire LHS will be 0. Entire LHS will be 0 with this substitution. Once again, I repeat, s tending to infinity, plugging over s infinity over here, this will be e raised to minus infinity, and that will be 0, and everything will be 0. That is it. All right, and over this side also, limit s tending to infinity, s into x of s. You may have something in your mind now, why don't we plug in infinity straight away over here? No, the existence of s over here depends on the ratio for x of s. Once you solve for when x of t is given, and when you evaluate for x of s, there is a chance of s getting cancelled, and so this won't be infinity. Some problem says that some given function, some x of t says that it exists, that doesn't become infinity, and minus x of 0 as it is. Why? Because we don't have any s term over here, so that remains as it is. And in RHS it's negative, pulling this x of 0 over this side, that will be positive, and guys, I am pulling over this one over this side. All right, so we don't have this anymore, in the sense that x of 0 is that one. And a small modification over here, plugging in t over here, guys, t, and we had t tending to 0 over here, and so limit t tending to 0, x of t, and limit s tending to infinity, it's initial value theorem. This has initial value theorem. When t tends to 0, s will be tending to infinity. All right, this is the result for what is that? Let me rewrite over here. Limit t tending to 0, x of t, we have limit s tending to infinity, x of s. That's it for initial value theorem. T equal to 0, that corresponds to initial value theorem. And now going for s tending to 0 in the above equation on both the sides. All right, so s tending to 0 can be plugged here, e raised to 0, that will be 1. All right, s tending to 0, in the sense plugging in 0 over here, this will be 0, e raised to 0, this entire term will be 1, and we will be left over with this one. In the sense, what else is left over here? It's integral 0 to infinity. No, thing is, this is 1, so this is the one, that's 1, and when that becomes 1, this is left over. And over this side, plugging in with what? Limit s tending to infinity this time. Infinity? No, s tending to 0, isn't it? 0, s into x of s minus x of 0 remains as it is. This is another result, don't get confused with this one. All right, and in this case it's dt. In this case, integration, and first derivative gets cancelled, x of t remains along with the limits. All right, so plugging in the limits, x of infinity minus x of 0, RHS we have limit s tends to 0, s into x of s. We cannot straight away plug in the value of s over here, making it 0. Why? Because existence of s over here depends upon the x of s value, the Laplace transform of x of t minus x of 0 as it is. All right, so something gets cancelled on either side, as we don't have this anymore. This one also doesn't exist anymore. So making over here t tending to infinity, and plugging in over t over here, t, and what else? Limit t tending to infinity, x of t, that will result to limit s tending to 0, s into x of s. That equation for final value. This gives the initial value, and this gives the final value. That's it.